Picture this. You're sitting in your chair right now, probably thinking you're completely still. But here's something that will shatter everything you think you know about reality. You are currently traveling through time, exactly the speed of light. Not metaphorically, literally. Every single second, you move 1 second into the future at the maximum possible speed through the temporal dimension. And here's where it gets absolutely insane. If you could somehow move faster than light through space, you wouldn't just break the laws of physics. You wouldn't just time travel. Something far more disturbing would happen. Time itself would cease to exist for you. Not slow down, not reverse. It would break, shatter, become mathematically undefined. What if I told you that the speed of light isn't really about light at all? It's the universe's speed limit for causality itself, the absolute maximum speed at which cause can lead to effect. And breaking that barrier doesn't just mean going really, really fast. It means destroying the very fabric of cause and effect that holds reality together. In the next 3 hours, I'm going to take you on a journey that will completely transform how you understand time, space, and your place in the cosmos. We're going to explore why faster-than-light travel isn't just difficult, it's philosophically, mathematically, and physically impossible in ways that will blow your mind. And by the end, you'll understand why this impossibility might be the most beautiful thing about our universe. But before we dive into this reality-shattering journey, do me a favor, hit that subscribe button and smash the like if you're ready to have your mind completely blown. And drop a comment telling me what country you're watching from and what time it is right now. I want to see how many different time zones we're connecting across as we explore why time itself is stranger than you ever imagined. Let's start with something everyone thinks they understand. Light is fast, really fast. About 186,282 miles per second, or roughly 300 million meters per second. But here's the twist that most people never learn in school. The speed of light has absolutely nothing to do with light being special. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would revolutionize physics forever. His name was Albert Einstein, and his theory of special relativity didn't start with studying light. It started with a simple thought experiment he'd been obsessing over since he was 16. What would you see if you could ride alongside a light beam? Think of it like this. If you're driving next to another car on the highway at the same speed, that car appears stationary relative to you, right? So if you could somehow match the speed of light, you should see the light wave frozen in space, like a stationary electromagnetic field. But here's the problem: Maxwell's equations, which describe how light works, don't allow for stationary light waves. They mathematically cannot exist. Einstein realized something profound. The speed of light isn't variable. It's constant, always, for everyone, no matter how fast you're moving. If you're standing still and measure light, it goes 186,282 miles per second. If you're in a spaceship going 99% the speed of light and measure that same light beam, it still goes 186,282 miles per second relative to you. Not 1% faster. Exactly the same speed. This is where things get weird. Really weird. Because if the speed of light is always constant, but you're moving at different speeds, something else has to change to make the math work. And that something is time and space themselves. Here's what will blow your mind. In 1887, 2 scientists named Albert Michelson and Edward Morley conducted an experiment that was supposed to detect Earth's motion through the luminiferous ether, a substance scientists believed filled all of space and carried light waves like water carries ocean waves. They built an incredibly precise device called an interferometer that could detect tiny changes in light speed as Earth moved through this ether. The result? Nothing. Absolutely nothing. No matter which direction they pointed their device, no matter what time of year, light always traveled at the same speed. The experiment was considered a failure at the time, but it was actually the most important null result in the history of physics. It proved that there was no ether, and that light speed was truly constant. But why? Why would the universe work this way? Here's where we need to understand something crucial. The speed of light, let's call it c like physicists do, is actually the speed of causality. It's the maximum speed at which any cause can produce an effect. It's the speed at which information itself can travel through the universe. Think of it like the universe's refresh rate. If reality was a video game, c would be the maximum frame rate at which the universe can process events. Not because of some technical limitation, but because of the fundamental structure of space-time itself. Now we're going to explore the first mind-bending consequence of light's constant speed: time dilation. And I promise you, this is going to challenge everything you think you know about time. Imagine you're on a train, holding a laser pointer aimed at the ceiling. You flash the light. It bounces off a mirror on the ceiling and comes back down. Simple, right? From your perspective on the train, the light travels straight up and straight down. Let's say the ceiling is 10 feet high, so the light travels 20 feet total. Now imagine I'm standing outside, watching your train zoom past at half the speed of light. From my perspective, the light doesn't go straight up and down. The train is moving, so the light traces out a diagonal path up and forward as the train moves, then down and forward. The light travels a longer distance from my perspective than from yours. But here's the critical part. We both measure the light moving at exactly the same speed, the speed of light, c. Same speed, but different distances. And since speed equals distance divided by time, if the light travels a longer distance for me, but at the same speed, then more time must pass for me than for you. This isn't an illusion. This isn't a measurement error. Time literally passes more slowly for you on the moving train than for me standing still. Your clock actually ticks slower. Your heart beats slower. You age slower. Not because the train ride is relaxing, but because time itself is moving differently for you. In 1971, physicists Joseph Haffel and Richard Keating proved this with a beautiful experiment. They synchronized 4 atomic clocks, the most precise timekeepers ever built. They left 2 on the ground and flew the other 2 around the world on commercial airplanes, one going east and one going west. When they brought all the clocks back together, the ones that had been flying were behind the ones that stayed on the ground. Not by much, we're talking billionths of a second, but exactly the amount Einstein's equations predicted. The clocks didn't malfunction. Time actually passed more slowly for them because they were moving faster. And here's what's truly mind-blowing. GPS satellites orbiting Earth experience this every single day. They're moving so fast that time passes more slowly for them than for us on the ground. Without correcting for time dilation, your GPS would be off by miles within hours. Every time you use Google Maps, you're relying on Einstein's equations about time being relative. But let's push this further. What happens as you approach the speed of light? The time dilation equation includes a term called the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who discovered it in 1892. The equation is gamma equals 1 skirt 1 v squared per c squared, where v is your velocity and c is the speed of light. At everyday speeds, this factor is essentially 1, meaning no noticeable time dilation. At 50% the speed of light, gamma is about 1.15 time passes about 15% slower for you. At 90% the speed of light, gamma is about 2.3 time passes less than half as fast. At 99% the speed of light, gamma is about 7 year for you equals 7 years for everyone else. But watch what happens as you approach exactly the speed of light. At 99.9% of c, gamma is 22. At 99.99%, it's 71. At 99.999%, it's 224. The curve shoots toward infinity. At exactly the speed of light, The Lorentz factor becomes infinite, meaning time would stop completely. And here's the kicker. What happens if you try to go faster than light? If v is greater than c, then v per c squared is greater than 1, which means you're taking the square root of a negative number. Time doesn't just stop, it becomes imaginary. Literally, as in the mathematical term for the square root of negative numbers. Time becomes undefined, impossible, broken. But before we can fully understand why faster than light travel breaks time, we need to understand the second massive barrier, energy. And this is where things get even more impossible. You probably learned in school that kinetic energy, the energy of motion, equals 1/2 mass times velocity squared. That equation works great for cars, baseballs, and rockets. But it's actually just an approximation that works at low speeds. The real equation, the one Einstein discovered, is far more revealing. Einstein's complete equation for kinetic energy includes that Lorentz factor we talked about. As you approach the speed of light, the energy required to keep accelerating doesn't just increase, it explodes toward infinity. Think of it like this. Imagine you're pushing a shopping cart. Easy, right? Now imagine the shopping cart gets heavier the faster you push it. Not just a little heavier, exponentially heavier. At 50% the speed of light, an object has about 15% more energy than its rest mass energy. At 90%, it has 230% more. At 99%, it has 700% more. At 99.9%, it has 2,200% more. The object doesn't just require more energy to accelerate, it effectively becomes more massive. And that increased mass makes it even harder to accelerate further. Here's the cruel joke the universe plays. As you get closer and closer to the speed of light, you need more and more energy to squeeze out each tiny bit of additional speed. To accelerate a single electron, one of the lightest particles that exists, to exactly the speed of light would require infinite energy. Not a lot of energy. Not more energy than exists in all the stars. Literally infinite energy. Mathematically undefined. Impossible. We see this every day in particle accelerators. The Large Hadron Collider near Geneva can accelerate protons to 99.9999991%, the speed of light. That's fast enough that if a proton could race light around Earth's equator, light would only win by about 6 centimeters per lap. But to get that last 0.0000009% closer to light speed would require more energy than humanity has ever produced in its entire history. Physicist John Bell, who made fundamental contributions to quantum mechanics in the 1960s, put it perfectly. Relativity tells us that as we try to accelerate something with mass to the speed of light, we're essentially trying to transform it into light itself. And matter isn't light. It can't be light. The universe simply doesn't allow that transformation. But wait, there's something even stranger going on. Remember that Einstein's famous equation E, q mc, tells us that mass and energy are equivalent? As you pump more energy into an object to make it go faster, that energy has mass. So you're not just pushing harder against a heavier object, you're making it heavier by the very act of trying to accelerate it. It's like trying to climb a mountain that grows taller with every step you take. Here's what will blow your mind. Light itself travels at the speed of light because photons have zero rest mass. They're pure energy. If a photon ever stopped moving, it would cease to exist. Light must travel at the speed of light. It has no choice. Anything with mass can never reach the speed of light, no matter how much energy you give it. Now we're getting to the really disturbing part. Even if you somehow had infinite energy and could magically accelerate past the speed of light, which you can't, you would create something far worse than a physics violation. You would break causality itself. You would make it possible for effects to precede their causes. Let me explain with a thought experiment that will scramble your brain. Imagine you have a faster-than-light phone. Let's call it an FTL phone. You're on Earth, and your friend is on a planet 4 light years away. At noon Earth time, you send your friend a message via this impossible FTL phone, and she receives it instantly. Seems innocent enough, right? But here's the problem. Simultaneously doesn't mean the same thing to everyone in a relativistic universe. There's a phenomenon called relativity of simultaneity that Einstein discovered. Events that appear simultaneous from one perspective don't appear simultaneous from another perspective if you're moving relative to each other. From your friend's perspective, if she's moving relative to Earth, your noon message might not arrive at her noon. Depending on her velocity, it might arrive at her 11 a.m. or her 1 p.m. or any other time. And here's where it gets truly insane. If she replies instantly with her own FTL message, her reply might arrive back at Earth before you sent your original message. You would receive her reply at 11:30 a.m. Earth time, 30 minutes before you sent your original message at noon. The effect her reply would precede the cause your initial message. This isn't just weird, it's logically impossible. It violates the fundamental principle that causes must come before effects. And it gets worse. Once you can send messages into your own past, you can create grandfather paradoxes. You could send yourself a message saying, "Don't send this message." If you receive it and obey, you never send it. So you never receive it, so you do send it, creating an infinite logical loop. Reality literally cannot accommodate this. In 1962, physicists Roger Penrose and E.C. George Sudarshan independently proved that faster-than-light travel or communication in any form would allow you to construct a scenario where information could be sent into the past. Not might allow would inevitably allow. This is called the tachyonic anti-telephone problem, and it shows that FTL travel doesn't just break physics, it breaks logic itself. Think of it like this. Causality is the glue that holds reality together. Every event is the effect of some prior cause. The sun fusion reactions cause light to travel to Earth, causing plants to photosynthesize, causing oxygen to be produced, causing you to breathe. It's an unbroken chain of cause and effect stretching back to the Big Bang. If effects could precede their causes, that chain would tangle into an impossible knot. You could literally have events that cause themselves, effects without causes, causes without effects. The universe would become a logical contradiction, like a square circle or a married bachelor. Here's something that should blow your mind. The speed of light isn't the speed of light, it's the speed of causality. It's the maximum speed at which one event can influence another event. Light travels at this speed because photons are massless and therefore must travel at the maximum possible speed. But C would exist even if light didn't exist. It's built into the geometry of space-time itself. To really understand why time breaks if you move faster than light, we need to stop thinking about space and time as separate things. They're not. They're part of a single, unified entity called space-time. And understanding this will completely transform your view of reality. Imagine you're looking at a map. You can move north-south or east-west or any diagonal combination. These are your 2 dimensions of space. Now imagine that time is a 3rd dimension, perpendicular to both. Every event in history, your birth, the extinction of the dinosaurs, the formation of the first stars, is a specific point in this 4-dimensional space-time. Your life isn't a 3-dimensional object moving through time. Your life is a 4-dimensional object called a world line, a snake-like path through space-time that starts at your birth and ends at your death. Right now, you're experiencing one particular cross-section of your world line. What you call the present is just your current position along that path. In 1908, mathematician Hermann Minkowski, who had been Einstein's professor, presented this revolutionary way of thinking about relativity. He famously declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Here's where it gets wild. In this space-time geometry, When you're sitting still, not moving through space, you're moving through time at maximum speed, advancing 1 second per second into the future at the speed of light. But when you start moving through space, you must move proportionally slower through time, because your total velocity through space-time must remain constant. Think of it like a car with the accelerator stuck at exactly 60 miles per hour. If you're driving due north, all 60 miles per hour goes into your northward motion. But if you turn the wheel and start heading northeast, that 60 miles per hour gets split maybe 40 miles per hour north and 40 miles per hour east. The exact numbers depend on angles, but you get the idea. Your speed in any single direction decreases because your total speed is fixed. The same thing happens with space-time. The more of your motion through space-time that's directed through space, the less is directed through time. At everyday speeds, this trade-off is imperceptible. But as you approach the speed of light, almost all your motion through space-time is directed through space, leaving almost none for motion through time. Time slows to a crawl. And here's the mind-blowing part. Light moves through space at exactly c, which means it uses 100% of its motion budget for spatial movement. That leaves exactly 0% for temporal movement. From a photon's perspective, if a photon could have a perspective, no time passes. A photon emitted from a star 1 billion light years away experiences its entire journey instantaneously. It's emitted and absorbed in the same instant from its own reference frame. Now, what would happen if you could somehow exceed the speed of light? You would be trying to move faster through space than the maximum allowed total speed through space-time. Mathematically, you would need to move backward through time to compensate, not just slow down reverse. The equations literally demand it. But backward motion through time creates all those causality paradoxes we talked about. So the universe has a simple solution. It doesn't allow faster than light travel. Not because it's difficult, but because it's meaningless, like asking what's north of the North Pole or what happened before time began. Let me introduce you to one of the most profound concepts in modern physics, the light cone. This single diagram will show you why faster than light travel isn't just impossible, it's nonsensical. It's like asking whether the color blue weighs more than Wednesday. Imagine you're at a specific point in space-time. Let's call it here and now. If you want to visualize this, picture a graph where horizontal represents space and vertical represents time. You are a single point on this graph. Now imagine light expanding outward from that point, in all directions, a growing sphere moving at the speed of light. If we collapse this to 2 dimensions for visualization, that expanding sphere of light looks like an expanding circle. As time moves upward on our graph, that circle grows, creating a cone shape. This is your future light cone, the set of all events in the universe that you could possibly influence. Everything inside your future light cone is reachable by you or by signals you send. Everything outside your future light cone is completely and utterly beyond your reach. You cannot affect it, communicate with it, or travel to it, ever, no matter what you do. Those events are not just distant, they're causally disconnected from you. Similarly, you have a past light cone extending downward, the set of all events that could have influenced you to get you to this moment. Everything that has ever affected you, every photon that's hit your retina, every sound wave that's reached your ear, every gravitational pull, every particle interaction comes from inside your past light cone. Here's what will blow your mind. The surface of your light cone, moving at exactly the speed of light, represents the absolute boundary between possible and impossible. Events on your light cone are reachable if you could travel at exactly c. Events inside are reachable if you travel slower than c. Events outside are unreachable, period. Now here's where things get philosophical. Most of the universe is outside your light cone. Right now, at this very moment, things are happening on a planet 1 million light years away. But those events are outside your present light cone. They cannot affect you. You cannot affect them. And in a very real sense, they don't exist in your reality yet. They will exist in your future light cone in 1,000,000 years, when light from those events finally reaches you. But right now, they're beyond the edge of your possible universe. The observable universe, the farthest we can possibly see, is just the portion of the universe within our past light cone. Currently, that's about 46.5 billion light years away, more than 13.8 billion, despite the universe being 13.8 billion years old, thanks to expansion. But that's another story. Everything beyond that might as well be in another universe entirely. We can never see it, reach it, or be affected by it. Physicist Brian Greene described light cones as the prison bars of the universe, except unlike normal prison bars, these are woven into the fabric of reality itself. You can't break through them because there's no through to break into. Outside your light cone isn't distant. It's undefined. If you could somehow travel faster than light, you wouldn't be traveling outside your light cone. That's not physically meaningful. Instead, you would be redefining what your light cone means, which would mean redefining causality, which would mean reality itself would need to reorganize around you. The universe simply doesn't allow this reorganization. Think of your light cone as the absolute boundary of what's real for you. Everything inside has either affected you or will be affected by you. It's part of your causal universe. Everything outside is as meaningless to you as events that never happen or places that don't exist. Faster than light travel would be like trying to visit a place that isn't just far away, but that literally doesn't exist in any meaningful sense. Now let's explore one of the most mind-bending ideas in theoretical physics. What if particles that travel faster than light already exist? These hypothetical particles are called tachyons, from the Greek word tachys, meaning swift, and understanding why they probably don't exist will show you exactly why faster than light travel breaks reality. The word tachyon was coined in 1967 by physicist Gerald Feinberg. Here's the wild thing. Einstein's equations don't strictly forbid faster than light particles. They just demand that if such particles exist, they must always travel faster than light and can never slow down below light speed, just as regular matter can never speed up beyond light speed. There would be an impassable barrier at sea, with normal matter below it and tachyons above it. But here's where the mathematics gets truly weird. For tachyons to exist, they would need to have imaginary mass. Not imaginary as in made up, but imaginary as in the mathematical term, the square root of a negative number. Their rest mass would be square root square meters. And particles with imaginary mass have some seriously disturbing properties. Remember that Lorentz factor equation? For normal particles, it grows toward infinity as you approach light speed. But for tachyons traveling faster than light, the Lorentz factor would be imaginary, involving the square root of a negative number. What does that even mean physically? Physicists honestly aren't sure. Here's what really breaks your brain. A tachyon moving forward in time would look identical to a tachyon moving backward in time, just from a different reference frame. An observer moving one direction sees a tachyon traveling forward through time from point A to point B. An observer moving the opposite direction sees that same tachyon traveling backward through time from point B to point A. This means tachyons could be detected before they're emitted. You could receive a tachyon signal before it was sent. You could observe effects before their causes. And we're back to those grandfather paradoxes that make reality logically impossible. In 1970, physicist G.A. Benford and his colleagues published a paper called Tachyonic Anti-Telephone that proved if tachyons exist, you could use them to send messages to your own past. Here's how. You send a tachyon signal to a friend who's moving relative to you. From their reference frame, they receive it before you send it. They immediately send a tachyon reply. From your reference frame, their reply arrives before your original message. You've created a closed time-like curve time machine. You could send yourself the results of tomorrow's lottery numbers. You could warn yourself about mistakes before you make them. You could create causal loops where information has no origin, like a book that writes itself, or a watch that's never manufactured, but just loops through time eternally. The universe has a simple solution to this paradox. Tachyons probably don't exist. Despite decades of searching, we've never detected a single tachyon. No particle accelerator has ever produced one. No cosmic ray detector has ever seen one. No telescope has ever observed any phenomenon that requires them. And here's the deeper truth. The fact that tachyons would break causality is probably why they don't exist. It's not that the universe coincidentally happens to forbid them. It's that the mathematical structure of causality itself forbids them. A universe with tachyons would be logically inconsistent. It would be a universe where reality contradicts itself. Think about what this means. The speed of light isn't just a speed limit for travel. It's a boundary between possible and logically impossible. On one side of that boundary, you have normal causality, causes precede effects, time moves forward, reality makes sense. On the other side, you have logical contradictions, temporal paradoxes, and the breakdown of reality itself. But wait, you might be thinking, what about all those science fiction concepts like warp drives, wormholes, and Alcubierre drives? Don't they allow faster than light travel without breaking causality? Well, this is where things get really interesting and really subtle. In 1994, physicist Miguel Alcubierre published a paper that shocked the physics community. He showed that Einstein's equations technically allow for a warp drive, a way to travel faster than light without actually moving faster than light. Mind-bending, right? Let me explain. Alcubierre's idea was brilliant. Don't move through space faster than light. Instead, compress space in front of you and expand space behind you, and surf the wave of distorted space-time itself. It's like being on a cosmic surfboard, riding a wave through space-time. Think of it like this. Imagine ants crawling on a rubber sheet. The ants can only crawl at a certain maximum speed. That's their speed of light. But if you could grab the rubber sheet ahead of one ant and scrunch it up, while stretching the sheet behind the ant could effectively cover huge distances without personally moving faster than its maximum crawling speed. The ant isn't moving through the rubber faster, the rubber itself is moving. Technically, this doesn't violate relativity. You never locally exceed the speed of light. In your little bubble of space, light still moves at c, and you're still moving slower than c, relative to the space immediately around you. But space itself is being warped so dramatically that you're effectively traveling faster than light relative to distant objects. Here's the problem. The energy requirements are absolutely insane. Alcubierre's original calculations suggested you'd need the mass energy equivalent of Jupiter just to create a warp bubble small enough for a spacecraft. Later refinements reduced this to merely the mass energy of several suns, still completely impossible with any technology we can imagine. But it gets worse. The type of energy you need is negative energy density, a kind of energy that pushes things apart rather than pulling them together. We've observed this in quantum mechanics in tiny amounts through something called the Casimir effect, discovered by Hendrik Casimir in 1948. But creating the amount needed for a warp drive? We don't even know if that's theoretically possible, let alone practically achievable. And here's the real kicker. In 2012, physicist Stefano Finazzi showed that Alcubierre drives would probably violate causality anyway. Observers in different reference frames would disagree about when the warp drive left and when it arrived, potentially creating time travel paradoxes. The universe's causality police always find the loopholes. Wormholes have similar problems. First proposed by physicist John Wheeler in 1957, though the mathematics goes back to Einstein and Nathan Rosen in 1935. Wormholes are shortcuts through space-time tunnels connecting distant regions of the universe. If you could create a stable wormhole between Earth and a star 100 light years away, you could step through and arrive almost instantly. And it's a huge but wormholes naturally collapse almost instantly, unless you stabilize them with exotic matter having negative energy density. We're back to needing impossible amounts of impossible energy. Plus, physicists Kip Thorne and Michael Morris showed in 1988 that if you could create a stable wormhole, you could turn it into a time machine by moving one end of the wormhole at high speed. And we're right back to causality paradoxes. Here's what this all means. The universe seems to have a cosmic censorship principle. Whenever we find a mathematical loophole that might allow faster-than-light travel or time travel, that loophole always requires impossible resources, or creates causality paradoxes, or both. It's like the universe is explicitly designed to prevent faster-than-light travel, no matter how clever we get. Think about it. Why would the universe be set up this way? Why would every possible workaround fail? The answer is profound because causality is fundamental. It's not a feature of our universe. It's what makes this universe possible. Without causality, without causes reliably preceding effects, there could be no structure, no patterns, no laws of physics, no coherent reality at all. Now we're going to dive into something that will really scramble your brain. The relationship between faster-than-light travel and information. Because at its deepest level, the speed of light isn't about energy or particles or time dilation. It's about information itself. What is information? In physics, information is any difference that makes a difference. It's the state of a system, the configuration of particles, the pattern of energy. And here's the crucial insight that physicist John Wheeler emphasized throughout his career. Information is physical. It's not some abstract concept. It's a real, tangible thing that obeys physical laws. In 1948, mathematician Claude Shannon, not to be confused with Claude the AI, founded information theory and proved something remarkable. Information has entropy. It has thermodynamic weight. When you erase information, you must dissipate heat. Information is as real as energy or matter, in fact. Many modern physicists believe information is more fundamental than either. Here's where it connects to light speed. Information cannot be transmitted faster than light. Not energy, not matter, not information. This is the deepest statement of relativity. If you could send information faster than light, you would be able to violate causality, creating all those paradoxes we've discussed. Think about what information really means. When you observe something, let's say you see a supernova explode, you're receiving information. Photons emitted by the explosion carry information about what happened. That information travels at light speed. The explosion itself, the actual physical event, also propagates at or below light speed as the shock wave expands. But here's the subtle part. The event isn't real to you until the information reaches you. From your perspective, the supernova didn't exist until you observed it. This isn't philosophical mysticism, it's basic causality. If something can't affect you, it might as well not exist in your reference frame. Now imagine you could somehow receive information faster than light, maybe through quantum entanglement, which we'll discuss more in a moment. You would be observing effects before their causes. You would know about events before they happened from certain reference frames. The very concept of now would become meaningless. In 1993, physicist Charles Bennett proved something called the no-communication theorem for quantum mechanics. Even though entangled particles can affect each other instantaneously across any distance seemingly, violating relativity, you cannot use entanglement to transmit information faster than light. The quantum states are correlated, but the correlation is random. You can't control it to send a message. It's like this. Imagine you and a friend each have a magic coin. When you flip yours and get heads, your friend's coin instantly shows tails, no matter how far apart you are. Sounds like instant communication, right? But here's the catch. You can't control whether your flip gives heads or tails. It's random. So you can't use it to send information. You can verify afterward that your flips were correlated, but you can't use the correlation to communicate. Every single attempt to transmit information faster than light through quantum entanglement, through wormholes, through warp drives, through any mechanism either fails or requires violating causality. The universe protects the speed of light barrier more fiercely than anything else. Why? Because information is causality. When information flows from event A to event B, it means event A can causally influence event B. The speed of light is literally the speed at which one part of the universe can know about another part. It's the speed at which reality propagates. Here's something that should blow your mind. When you look at the night sky, you're not seeing the universe as it is now. You're seeing a patchwork of different times. The moon you see is 1.3 seconds old. The sun is 8 minutes old. The nearest star, Proxima Centauri, is 4 years old. The Andromeda Galaxy is 2.5 million years old. The most distant galaxies we can see are over 13 billion years old. There is no now that encompasses the whole universe. Now is local. Your now is different from someone else's now if you're moving relative to each other. The universe doesn't have a universal clock. Time is as local and personal as your location in space. If faster-than-light travel were possible, now would be meaningful across the whole universe. You could establish a universal reference frame, but you can't, because you can't. The universe is fundamentally relativistic. There is no privileged now, no universal present moment, no objective time. Time is relative, personal, local. And faster-than-light travel would violate that fundamental truth. I know what you're thinking, but what about quantum entanglement? Doesn't that allow instant communication across any distance? Doesn't that violate the light speed limit? This is one of the most common misconceptions in all of physics. So let's clear it up with a deep dive into one of the strangest phenomena in the universe. Quantum entanglement was famously called spooky action at a distance by Albert Einstein, who is deeply troubled by it. Here's what happens. Two particles can be created in a shared quantum state, such that measuring one instantly affects the other, no matter how far apart they are. Measure one particle's spin as up, and the other instantly becomes down, even if it's on the other side of the galaxy. In 1964, physicist John Bell proved with his famous Bell's theorem that this effect is real. It's not just that we don't know the states until we measure them. The particles genuinely don't have definite states until measurement, and the measurement of one truly affects the other instantaneously. Experiments by Owing Aspect in 1982 confirmed this beyond any doubt. The effect is real, it's instant, and it's non-local. So why can't we use this for faster-than-light communication? Here's the cruel trick. The results are random. Completely, fundamentally, quantum mechanically random. Think of it like this. You and your friend each have a magic box. When you open yours and find a red ball, your friend instantly finds a blue ball in theirs. Open, close, open again, always opposite colors. But here's the catch. You can't control what color you get. It's random. Half the time you get red, half the time blue. Your friend's results are perfectly correlated with yours, but both of you are seeing random sequences. Can you send a message? No, because from your friend's perspective alone, they just see a random sequence of red and blue. They'd need to compare their results with yours, using normal, slower-than-light communication, to even discover the correlation exists. The correlation is only meaningful in hindsight. Physicist David Merman put it perfectly. Quantum mechanics provides correlations without causation. The particles are correlated, their states are linked, but you can't use that link to transmit information because you can't control the states. Information still can't travel faster than light. But here's where things get philosophically deep. Entanglement shows us that the universe is fundamentally non-local at the quantum level. Parts of the universe that are separated by vast distances can still be intimately connected. But this non-locality doesn't violate relativity because it can't be used to send information. It's like the universe is playing a carefully balanced game. It allows quantum weirdness particles being in multiple states at once, instant correlations across space, but it does so in exactly such a way that causality and relativity remain intact. Every time quantum mechanics seems like it might allow faster-than-light communication, there's always a catch that preserves the light speed limit. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experimental work on quantum entanglement. Their experiments proved beyond any doubt that quantum mechanics really is as weird as it seems. But they also proved that even this weirdness respects relativity. Here's what this tells us. The speed of light limit isn't some arbitrary rule the universe follows. It's woven into the deepest fabric of reality. Even quantum mechanics, the most successful theory in all of science, which routinely violates our intuitions, respects the light speed barrier. Why? Because that barrier is causality itself. Think about the implications. We live in a universe where distant parts can be mysteriously connected, where particles can affect each other instantly, where reality is fundamentally probabilistic and weird. Yet even with all that quantum strangeness, you still can't send information faster than light. You still can't violate causality. The universe protects that principle absolutely. Now let's explore one of the most famous thought experiments in relativity, the twin paradox, because it reveals something profound about the asymmetry of time and why faster-than-light travel would create impossible contradictions. Here's the setup. Two twins, Alice and Bob, are on Earth. Alice gets in a spaceship and travels to a star 10 light-years away at 80% the speed of light, then immediately turns around and comes back at the same speed. Bob stays on Earth. When Alice returns, how much time has passed? For Bob on Earth, the math is simple. Alice traveled 10 light-years out and 10 light-years back at 0.8 c. That's 25 years total. But Alice experiences time dilation. At 80% the speed of light, the Lorentz factor is about 1.67, so time passes about 60% as fast for her. She only experiences 15 years of time. When Alice returns, she's 10 years younger than Bob, not metaphorically, literally. Her heart beat fewer times. Fewer cells died and were replaced. She experienced fewer moments. This isn't science fiction. It's what would actually happen if we could build such a spaceship. But here's the paradox that confused people for decades. From Alice's perspective, isn't Bob the one moving away at high speed? Shouldn't Bob be the one who ages less? Both see the other moving, so why isn't it symmetric? The resolution discovered early on by Einstein and others is that the situation isn't symmetric. Alice accelerates. She turns around. She changes reference frames. Bob doesn't. The acceleration breaks the symmetry, and acceleration is absolute in a way that velocity isn't. Alice feels forces. Bob doesn't. Alice is the one who ages less. This has been confirmed by actual experiments. In 1971, the Haefel-Keating experiment I mentioned earlier not only confirmed time dilation, but also showed this asymmetry. The clocks that flew around the world aged differently than the ones that stayed still, even accounting for their direction of travel. But here's where it connects to faster-than-light travel. Imagine Alice could somehow travel to that star instantly faster than light. She arrives before light from her departure has time to reach the star. From certain reference frames, she would arrive before she left. The cause, her departure, would come after the effect, her arrival. Now she instantly returns to Earth, again faster than light. Depending on her exact speed and reference frames involved, she could arrive back on Earth before she left. She would meet herself. She could prevent herself from leaving. creating a grandfather paradox. The mathematics of relativity are crystal clear on this. If you could travel faster than light, you would necessarily be able to travel into your own past. Not might be able to, would inevitably be able to. Any faster than light travel is equivalent to time travel, which means it's equivalent to causality violation. Physicist Paul Davies wrote in 2002, "The reason faster than light travel is impossible isn't that we lack the technology or the energy. It's that faster than light travel is equivalent to time travel, which is equivalent to logical contradiction. The universe doesn't prohibit it because it's difficult. The universe prohibits it because it's meaningless." Think about what the twin paradox really shows us. Time is not just a dimension we move through. It's intimately connected to acceleration, to gravity, to motion through space. When Alice accelerates, she's literally changing how time flows for her relative to Bob. She's taking a shorter path through space-time. In space-time geometry, Alice and Bob follow different world lines, different paths through the four-dimensional fabric of the universe. Alice's world line involves acceleration and curves through space-time. Bob's world line is straight, and in the bizarre geometry of space-time, the curved path is actually shorter in the time dimension. If Alice could move faster than light, she wouldn't be taking a shorter path through space-time. She'd be trying to go outside space-time altogether. But there is no outside. Space-time is all there is. Trying to move faster than light is like trying to go north of the North Pole. It's not just impossible. It's not even wrong. It's a category error. Now I'm going to blow your mind with an apparent contradiction. There are parts of the universe moving away from us faster than light right now. And this doesn't violate relativity at all. Understanding why reveals something profound about the difference between motion through space and the motion of space itself. The universe is expanding. This was discovered by Edwin Hubble in 1929, though evidence was building for years before. As space itself expands, distant galaxies move away from us. The farther away they are, the faster they recede. And beyond a certain distance currently, about 14 billion light years, galaxies are receding faster than light. Wait, what? How can anything move faster than light? Here's the crucial insight. These galaxies aren't moving through space faster than light. Space itself is expanding between us and them. It's like dots on a balloon being blown up. The dots don't move across the rubber, but they get farther apart as the rubber stretches. Relativity says nothing can move through space faster than light locally. If you're next to a galaxy, you can't zoom past it faster than light. But relativity says nothing about how fast space itself can expand or contract. The expansion of space isn't motion through space, it's the creation of new space. This means there are galaxies we can see, because their light was emitted when they were closer, that we can never reach, even if we left right now, traveling at the speed of light. The space between us and them is expanding faster than we could traverse it. It's like trying to walk up an escalator that's going down faster than you can climb. Currently, anything beyond about 16 billion light years is forever beyond our reach. Even at light speed, we could never get there because the intervening space is expanding too rapidly. These regions are outside our future light cone. They're causally disconnected from us forever. But here's what's truly mind-bending. When we see the light from these distant galaxies, we're seeing them as they were billions of years ago. The galaxy we're observing has long since moved beyond where its light came from. In fact, the galaxy is now in a region of space that's receding faster than light, which means new light being emitted from it now will never reach us. We're seeing ghosts' ancient light from regions now forever inaccessible. Physicist Lawrence Krauss calculated that in about 100 billion years, due to accelerating expansion driven by dark energy, all galaxies outside our local group will have receded beyond our cosmic horizon. Future astronomers would see a universe containing only our local cluster, surrounded by empty space. They would have no way to discover that the universe is expanding because everything they can see would be gravitationally bound and not expanding. We happen to live in a special time late enough that we've evolved intelligence, but early enough that we can still observe the expansion and the cosmic microwave background that tells us about the Big Bang. We can discover the deep truths about the universe's origin and evolution. In 100 billion years, that knowledge would be impossible to obtain. But I digress. The point is, the expansion of space doesn't violate relativity because nothing is moving through space faster than light. Space itself is expanding. It's like the difference between a car driving across a map versus the map itself being stretched. And here's the crucial distinction. When space expands, causality is still preserved. Information still can't travel faster than light through space. A supernova in a galaxy 15 billion light-years away still takes 15 billion years for its light to reach us, even though the galaxy is now much farther away due to expansion. The light traveled at sea through space for the entire journey. So faster-than-light recession due to cosmic expansion doesn't break causality, but faster-than-light travel through space would. One is the expansion of the stage. The other would be moving across the stage too fast. The universe allows the first, but absolutely forbids the second. Let's step back and ask the deepest question. Why does the speed of light have the specific value it has? Why 186,282 miles per second and not something else? And what would the universe be like if the speed of light were different? Here's something that will blow your mind. The speed of light isn't fundamentally about speed at all. It's about the relationship between space and time, between energy and momentum, between electricity and magnetism. The value of c appears in equations throughout physics, not because everything is somehow related to light, but because c is a fundamental conversion factor, woven into the structure of space-time itself. In fact, if we use what are called natural units, the unit system physicists use in theoretical work, we simply set c equals 1. Space and time have the same units. A distance of 1 light-year equals a time of 1 year. Energy and mass have the same units. Since E equals mc and c equals 1, we get E equals m. The speed of light is just the number that converts between these quantities. In these natural units, asking why is the speed of light 299,792,458 meters per second is revealed to be an arbitrary question. That number depends on our human-defined units of meters and seconds. The real question is, why do space and time have the relationship they do? And here's the profound answer. They have to have some relationship. The universe needs conversion factors between different types of quantities. What we call the speed of light is really just the universe's fundamental scaling factor, the number that relates space to time, mass to energy, electric fields to magnetic fields. Physicist John Wheeler spent decades thinking about this and concluded, the speed of light is not a law. It's a definition. It's the universe defining what we mean by space and time. We measure speeds in meters per second, but we could just as easily measure everything in natural units, where c equals 1 and speeds are dimensionless, numbers between 0 and 1. But what if c were different? What if the universal speed limit were faster or slower? This is where things get interesting. If c were much faster, say, infinite and all reference frames would agree on simultaneity. There would be a universal now throughout the cosmos. Time wouldn't dilate. Paradoxes would become possible. In fact, physicists have shown that if c were infinite, the universe would be mathematically inconsistent. Causality would break down. Effects could precede causes. The universe wouldn't make logical sense. If c were much slower, say, the speed of sound then, relativistic effects, would be part of everyday life. Walk across the room and your time would noticeably dilate. Throw a baseball and its mass would increase. Look in different directions and you'd see different rates of time flow. The universe would be nightmarishly complicated. The speed of light has to be finite, otherwise causality breaks. And it has to be fast enough that the universe is navigable and comprehensible at human scales. Otherwise, intelligent life probably couldn't evolve. We exist at exactly the right scale in a universe with exactly the right fundamental constants to make our existence possible. This is called the anthropic principle, and it's controversial among physicists. But one thing is clear: the value of C isn't arbitrary. It's precisely tuned to allow for a universe with structure, causality, and ultimately observers like us who can ponder these questions. Think about it. If faster-than-light travel were possible, then causality would be optional. Effects wouldn't need to follow causes. Information could influence its own past. The universe would be a chaotic mess where nothing made sense. The very fact that we exist in a comprehensible universe proves that faster-than-light travel is impossible. The speed limit isn't a restriction. It's what makes reality possible. It's what allows the universe to have structure, patterns, laws. Without the light speed limit, there would be no physics, no chemistry, no biology, no us. Let's bring this back to Earth literally and explore what the light speed limit means for humanity's future. Because even though we can't break this cosmic speed limit, it shapes everything about our potential as a spacefaring species. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. Even if we could build a spacecraft that travels at 10% the speed of light, which would be an absolutely incredible achievement, it would take 42 years to get there. The travelers would experience slightly less time due to time dilation, but only about 41.5 years. Not a huge difference at that speed. At 50% of light speed, the journey drops to 8.5 years. But the travelers would only age about 7.4 years due to more significant time dilation. At 90% of light speed, the journey is 4.7 years for stationary observers, but only about 2 years for the travelers. The closer you get to light speed, the more dramatic the time dilation effect. This is both humanity's curse and our blessing. The curse: we can never explore the universe quickly. No matter how advanced our technology becomes, traveling between stars will always take years at minimum, often centuries or millennia. We'll never have Star Trek-style instant travel to distant worlds. The blessing: if we could somehow achieve near-light speed travel, the travelers themselves would experience much less time than passes on Earth. A journey to a galaxy millions of light-years away would take millions of years from Earth's perspective. But the travelers could experience it as just a few decades if they traveled close enough to light speed. But here's the emotional impact this has. Those travelers could never come home. By the time they arrived, everyone they knew would be dead for millennia. Earth's entire civilization might have risen and fallen multiple times. They would be the ultimate immigrants, not just to a new place, but to a new time. Several science fiction authors have explored this poignantly. In Joe Haldeman's The Forever War, soldiers travel at near-light speeds to fight in an interstellar war. Each battle is decades or centuries apart from Earth's perspective, though only months pass for the soldiers. They return to find Earth completely unrecognizable, their families long dead, their world transformed beyond recognition. They become temporal refugees. Physicist Kip Thorne calculated that with sustained 1-gram acceleration, comfortable Earth-like gravity, a spacecraft could reach the center of the Milky Way in just 20 years of ship time. Even though 30,000 years would pass on Earth, the travelers would age only 20 years. But they could never return to anything resembling the civilization they left. This imposes a profound limitation on human expansion. We can spread through the galaxy, but we can never maintain a unified civilization. The light speed limit ensures that different colonies will evolve independently. Communication will always be delayed by years or centuries. Trade will be impossible for anything except information. Each world will be alone. Isaac Asimov explored this in his Foundation series, where faster-than-light travel allowed a galaxy-spanning empire. But in our real universe, such an empire is impossible. The Milky Way is 100,000 light-years across. Even light takes 100,000 years to cross it. A message from one side of the galaxy to the other would take 100,000 years minimum. No empire, no government, no organization could function on those timescales. Instead, humanity's future, if we become spacefaring, is one of fragmentation. Each colony world would be essentially on its own. They might share a common cultural heritage from Earth, but they would diverge rapidly. In 1,000 years, they might be unrecognizable to each other. In 10,000, they might not even think of themselves as the same species. The light speed limit doesn't just restrict how fast we can travel. It restricts how connected we can remain. It ensures that intelligence in the universe is inherently isolated. Each civilization exists in its own bubble of causality, unable to communicate faster than light with distant neighbors. And here's the sobering thought. This probably applies to all civilizations in the universe. If faster-than-light travel is impossible for us, it's impossible for everyone. There are no aliens with magic technology that bypasses these laws. Everyone faces the same limitations. The universe is probably teeming with life, but that life is fundamentally isolated by the speed of light. We are islands of consciousness in an ocean of space, forever unable to reach each other in meaningful ways. We're approaching the end of our journey, and I want to leave you with a different perspective on the light speed limit. Because while it seems like a prison, a cosmic constraint on our potential, it's actually something beautiful, something necessary, something that makes the universe not just possible, but meaningful. Imagine a universe without the light speed limit. Imagine that faster-than-light travel were possible. Here's what would happen. First, causality would be optional. Effects could precede causes. Information could influence its own past. Every event could potentially be in a causal loop with every other event. There would be no clear arrow of time, no definitive sequence of events, no objective history. The past would be as mutable as the future. Second, there would be no local reality. Everything would be instantly connected to everything else. There would be no here that's separate from there. No privacy, no independence. No individual existence separate from the whole. You wouldn't be a distinct person. You'd be an inseparable part of a cosmic whole where distinctions blur and identity becomes meaningless. Third, there would be no discovery, no exploration, no sense of wonder about what lies beyond the horizon. If you could instantly travel anywhere, everywhere would be essentially local. The universe would be small, finite, boring. There would be nothing distant to dream about, no unknown territories to inspire us. Fourth, and most profoundly, there would be no time in any meaningful sense. Time exists because causes precede effects, because past is different from future, because change happens in a definite sequence. Without the light speed limit, all moments would be essentially simultaneous, all places essentially adjacent. The rich tapestry of history would collapse into a single eternal now. The light speed limit gives us time. It gives us causality. It gives us locality, the fact that you are here and I am there, that we are distinct beings with separate experiences. It gives us privacy, independence, individual existence. It gives us a universe large enough to explore, mysterious enough to inspire wonder, structured enough to be comprehensible, yet complex enough to be interesting. Physicist Frank Wilczek won the Nobel Prize in 2004 for his work on quantum field theory. He wrote, "The speed of light is not a limitation, it's a liberation. It's what allows distinct events, separate places, individual minds. Without it, there would be no structure, no form, no meaning. The light speed limit is what makes the universe beautiful." Think about what time means. It means that causes precede effects. It means that your choices matter because they shape a future that doesn't yet exist. It means that history is real, that the past genuinely happened, that events have a definite sequence. All of this requires the light speed limit. All of this collapses without it. And here's the most beautiful part. The light speed limit ensures that we live in a universe of horizons. There are always places we haven't seen, events we haven't experienced, questions we haven't answered. The universe remains mysterious, not because we're ignorant, but because mystery is built into its structure. Beyond our horizon are things we cannot know, places we cannot reach, events we cannot influence. And that's glorious. We are local, finite, limited, and that makes our existence meaningful. If we could be everywhere, we would truly be nowhere. If we could know everything, we would truly understand nothing. If we could do anything, nothing we did would matter. Our limitations make us real. The light speed limit isn't a cage. It's the framework that allows consciousness, choice, meaning, beauty, and wonder to exist. It's what makes you distinct from me, what makes now different from then, what makes here separate from there. It's what allows there to be a universe at all, rather than an undifferentiated cosmic soup of possibilities. So let me bring this full circle to where we started. You are sitting somewhere right now, thinking you're standing still, but you're not. You're moving through space-time at exactly the speed of light. All your motion through space-time, 100% of it is currently directed through the time dimension. You're racing forward through time at the maximum possible speed. Every photon that hits your eyes, every sound wave that reaches your ears, every touch you feel, all of it propagates at or below the speed of light. You exist in a bubble of causality, defined by that speed limit. Everything inside your light cone is real to you. Everything outside doesn't exist in your present reality. And here's what I want you to understand. This isn't a deficiency. This is what makes your experience possible. You have a past because causality flows at light speed. You have a future because information about that future can't reach you faster than light. You have a present because you're at a specific location in space-time, separated from other locations by the finite speed of causality. When you look at the stars tonight, you're not seeing the universe as it is now. You're seeing ancient light, messages from the past arriving at exactly the speed the universe allows. That star might not exist anymore. That galaxy might have moved. The universe you see is a patchwork of different times, all woven together by the constant speed of light. And that's beautiful, because it means the universe is large enough that light takes billions of years to cross it. It means there are mysteries beyond your horizon. It means there are things you cannot know, places you cannot reach, futures you cannot predict. It means you live in a universe of wonder, discovery, and possibility. The light speed limit doesn't restrict you. It defines you. It makes you possible. Without it, there would be no you, no me, no Earth, no stars, no time, no space, no reality. The fact that you can't travel faster than light isn't a bug in the universe. It's the fundamental feature that allows the universe to exist. You are a pattern of matter and energy moving through space-time at the maximum possible speed through time. You are a process, not an object, a verb, not a noun, a journey, not a destination. And that journey is constrained and enabled by the speed of light, the universal speed limit that makes causality, time, space, and consciousness possible. So the next time someone asks why we can't travel faster than light, you'll know the answer isn't because we lack the technology or because we need too much energy. The answer is deeper and more beautiful, because faster than light travel would mean the destruction of causality, the breakdown of time, the end of meaning, and the collapse of reality itself. We can't go faster than light because time, this magnificent dimension we experience moment by moment, only exists because we can't. You live in a universe that makes sense, where causes precede effects, where the past is fixed and the future is open. Where you are separate from me, here is distinct from there, and now is different from then. And all of that, every bit of it, depends on one simple fact. Nothing can travel faster than light. That limit isn't a prison. It's the architecture of reality. It's what makes your existence possible. It's what makes the universe comprehensible, beautiful, and meaningful. And that, I think, is the most profound truth in all of physics. Thank you for taking this journey with me through space-time. If this expanded your mind, hit that like button, subscribe for more deep dives into the nature of reality, and share this with someone who's ready to have their understanding of time completely transformed. And remember, you're not just in the universe. You're part of it. You're made of stardust moving through space-time at the only speed that makes existence possible. And that's pretty incredible.